Hi, welcome back. Today we're going to talk about solving polynomial equations from the perspective of linear algebra. All right. And we'll see that as we develop kind of a very nice matrix to accompany a polynomial, that it will lead into some kind of important abstract mathematics on quotient vector spaces that will take up the next lecture and a half or so. Okay, so let me just remind ourselves where we are from the last lecture. We have a univariate polynomial, p, in R adjoint x, so it's in one variable x. Then there are some cases where we know that it's possible to just find the roots of p just mechanically, right? If it's linear, you can just solve for the roots. If it's quadratic, then you can use the quadratic formula to find all of the roots of p. It turns out there are formulas for cubics and for quartics. And there's a very deep result in modern algebra, which says that actually for degree 5 and higher, in general, you can't hope to solve a general quintic using finitely many steps involving just addition, multiplication, subtraction, division, and taking nth roots. So today, we're going to learn a linear algebra perspective on how to think about solving a polynomial. And it's still true that we're not, in general, going to be able to find the roots exactly of a degree 5 polynomial, because if you could, then you could do it for a degree 5 polynomial, which you can't. However, being able to think about things in the linear algebra perspective might give you a different way to look at algorithms to try to find the roots of a polynomial. That's the whole point. Okay, and to develop this notion of quotient vector spaces very naturally from this idea. Okay, so here's the idea. Right, if p is a polynomial in R join x in one variable, then to solve p of x equals 0, in other words, to find the roots of p, we could do the following, right? Find a matrix A such that p is the characteristic polynomial of A. Let's call this A sub p because it will depend on p. Then the roots of p are the same thing as the eigenvalues of AP. Or if I'm going to be even more specific, let's say that this thing has degree d, and then this matrix then would have to be d by d, right? Because I want p to be the characteristic polynomial of AP. But it'll be since polynomial is a finite sum, it has a finite degree, it'll be a finite size matrix if I can find it. Okay, and I should point out that it's actually not obvious at first whether or not such a matrix exists, or if it sometimes exists, or if it always exists. Right? Certainly it sometimes exists, because you take any matrix, you compute its characteristic polynomial, you get a polynomial. Right? So, but how do you know that you can get any polynomial that you want? Right? There's infinitely many polynomials. The degree gets very, very high. How do we know that there's always a matrix that will give us the characteristic polynomial being any polynomial we want? So is this possible? And the answer is actually yes. And it's not that obvious, but we'll write down a matrix that has exactly the characteristic polynomial for any polynomial p that we choose. And then it turns out that finding the roots of a polynomial is an equivalent problem to being able to find eigenvalues of a matrix, because every polynomial comes as the characteristic polynomial of the matrix. Any matrix has a characteristic polynomial, right? Of course, more than one matrix can have the same characteristic polynomial. So it's not like there's every polynomial gives you just one matrix, but you can always find at least one matrix that has that characteristic polynomial. Okay, so I'm about to give you the complete answer. We should try to understand why it works. So let's start with a polynomial, a general degree d polynomial. Again, it looks like this, where we just use the variables AD down through A0 to represent the coefficients. And what we do is we set up the following d by d matrix. So that it has a chance to have a degree d characteristic polynomial. And what you do is you put zeros along the diagonal almost everywhere, okay, except not at the very last column. So I'll have d minus 1 zeros. Then you put ones underneath the 0. There. Okay, so one's one step below the diagonal. And then in the last column, you put the following thing. You put negative a0 over ad, negative a1 over ad, dot, 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 down to negative ad minus 1 over ad, and then negative ad minus 2 over ad. Okay, I really should have wrote this clearer. So let me write it clearer. Negative a1 divided by ad, negative a2 divided by ad, dot, dot, dot. The last one is negative ad minus 1 divided by ad, negative ad minus 2 divided by ad. Okay, and this is basically just the answer. It turns out, and we're going to try to understand this, that the determinant of this matrix P, AP, is either plus or minus the polynomial that we want. Okay, but of course, if you're just interested in finding the roots of P, then that's the same thing as the roots of minus P. Okay. Hence, the roots of P are exactly the same thing. The eigenvalues of this matrix AP. Okay, so for that reason, this matrix here is called the companion matrix of P, or the companion matrix to P. Because it's a matrix that has exactly the eigenvalues that are the roots of polynomial P. In other words, the characteristic polynomial of AP is basically P, right? Now, we will try to understand this in two ways. The first way is we're going to just try to take the determinant of this matrix in a mechanical way. Technically, you need to use induction to do it properly, but then we're going to spend some time talking about quotient vector spaces, which will be a totally new topic to almost all of you. And we'll see another reason why this matrix has the determinant that is the polynomial that you want. Okay, but the very first thing we should do is we should make sure that this makes sense for our example polynomial from last time, right? So maybe I'll grab this so that we have it on the next slide. Right, and let's take our favorite polynomial from these lectures, which is this, x to the 5th minus 20x to the 4th plus 8x squared minus 10. Right, so what should the companion matrix to this thing be? It's going to be a 5 by 5 matrix. So 1, 2, 3, 4, 5. Let's make it 5 squares by 5 squares on this thing. Okay, it has zeros along the diagonal, so along the diagonal until the very last column. It has ones underneath. Okay, it has zeros everywhere else, of course. And then in this last column, you take negative, wait, I wrote something wrong. Right, this should be negative a0 over ad, negative a1 over ad, yeah, because we need to have d entries. So make sure to correct that in your notes. a1 over ad, right. So in this last column, you want to take negative a0, which is the constant term, divided by ad, which in this case is 1. So in this case, I don't actually need to divide anything. I'll need to divide them all by 1, so I can sort of ignore that. And sorry, I'm just realizing that this probably is not that visible. Let me do it bigger. Let's do it correctly and larger. Okay, so it's going to be a 5 by 5 matrix. So let me just give myself some numbers so I know where the rows and the columns are. Right, it has 4 zeros going down the diagonal, it has ones underneath it, and then this column is the column that we're trying to figure out, and you just take negative of each coefficient divided by 1 in this case. So you'll just take 10, that's negative 10. The next coefficient is the thing on the x term, but there is no x term, so that's 0. The next one, I need -8 because I have a coefficient of 8 there. Then I'll take 0 because that's the x cubed term. And then I'll take -20, which is +20. Okay, then I'll fill out the rest of this with zeros for completeness. And this is our companion matrix, AP. Okay, and so we're claiming that AP, its eigenvalues are exactly the roots of P of x. In other words, AP will have a characteristic polynomial that's a scalar multiple of P of x. And we should check to make sure this is true. And of course, we don't want to do this example by hand. It's a fixed small example, but bigger than I want to do by hand. So we should do this in Julia. So let me switch to the view of my laptop where we'll type this into Julia. Okay, so I'm now viewing the JL file that I'm going to load into Julia. That way I don't need to type directly into Julia. And we're using a new package. We're using the polynomials package in Julia. So I'm starting with using polynomials. And if this is the first time you're using it, you may need to install it. So you, if you try to use it and it doesn't have it, it will give you the command to install it. Okay, we still want to use linear algebra. And now this is how the polynomials package of Julia can read in a polynomial. So I'm going to let P be a polynomial. And the way that you instantiate it actually uses this thing we've been talking about the whole time, which is the fact that you can view polynomials as vectors, right? In other words, you feed in the coefficient vector of your polynomial, and Julia assumes that the first term is the constant term, the second term is the x term, the third term is the x squared term, the x cubed term, the x to the fourth term, and the x to the fifth term. And since I'm feeding in a vector in R6, it knows that it's a degrees 5 polynomial. Okay, so since every polynomial has finite degree, you can always instantiate it with a vector like this, starting with a constant term. Okay, and then I also want to read in our companion matrix that we just computed, right? So there are ones below the diagonal, and then going down the column, you get the negative of these first 5 terms, right? 10, 0, -8, 0, +20. Okay, so now I'm in my console window. I've gone to the directory that has my Julia file that I want, right? Lecture 18.jl. So let's run Julia. And let's include lecture 18.jl. Okay, so let's make sure that Julia read in everything correctly. In other words, that I typed it in correctly. So our polynomial P was supposed to be this one. And note, this is the polynomial that we want, right? X to the fifth minus 20x to the fourth plus 8x squared minus 10. And then the matrix, we called it A. So let's make sure that A is indeed the companion matrix. It has one below the diagonal, and then the negative coefficients going down the last column. Okay, and so we're claiming that the roots of P are the same thing as the eigenvalues of A. Now there's a very nice picture in the notes of the polynomial P, where you'll see that the graph only crosses the x-axis once, like a little bit before 20. And it gets kind of close near 0, but doesn't actually cross the axis. So since it's a degree 5 polynomial with a one real root, it looks like, because it also doesn't bounce off the axis, it just goes straight through the axis, so it seems like it's going to be one real root, and then you should get 4 complex roots that occur in 2 conjugate pairs. That's what we should expect for the roots of P, based on the graph. So let's take a look at the roots of P by just typing in roots, open parentheses, P, close parentheses. And Julia gives it to us as a vector. So notice that this is a complex conjugate pair of roots. This is a complex conjugate pair of roots. And this is a real root just a little bit below 20. So that's what we expect for the roots of the polynomial P. We also know how to find the eigenvalues of the companion matrix. Just type in eigenvals A. And you'll see that you get exactly the correct eigenvalues for A. So at least in this example, the thing that we claimed was the companion matrix does have the correct eigenvalues, exactly the roots of P. Okay, but let's try to understand why this is true. First, by trying to take the determinant, and second, by moving into quotient vector spaces. Okay, so now let's actually try to take the determinant of a companion matrix and just see why we get the polynomial that the matrix is a companion for. Okay, so if you want to understand something, what you should start by doing is by considering some small cases. Okay, so if we first consider, let's say, the 3 by 3 case, in other words, a degree 3 polynomial. What's the companion matrix? It's 0, 1, 0, 1, and then negative a0 over a3, negative a1 over a3, negative a2 over a3. That's our companion matrix. And so you want to find the characteristic polynomial of it. You want to take determinant of a minus lambda I. Right? So really what we want to do is we want to take the determinant of this with negative lambdas on the diagonal. So what we'll do is we'll take a cofactor expansion down the first column. Okay, so the determinant of this is negative a0 over a3 times the determinant of the submatrix that you get when you delete that row in that column. Which, if I delete this row and this column, I'm left with 1, 1, negative lambda. Okay, now the next term comes from plus a1 over a3 because you need to alternate the signs. And I should take the determinant of the remaining submatrix. So in this case, let's use this color for what we strike out. So what we're left with is negative lambda 0, 0, 1. Right, and then minus a2 over a3 minus lambda, this whole thing, right, times, if I delete now the purple row and the purple column, I get negative lambda 1, 0. This is the characteristic polynomial of that companion matrix in the 3 by 3 case. Okay, well, the determinant of the first matrix is just 1. Right? So what we'll get is we'll get negative a0 divided by a3. The second matrix has a determinant that's negative lambda. So you get minus a1 over a3 lambda. And the third matrix has determinant lambda squared. Maybe I'll just do it like this. Here's negative lambda, here's lambda squared. So what you get is you get plus negative a2 over a3 minus lambda times lambda squared. So in the end, what you get is you get negative lambda cubed minus a2 over a3 lambda squared minus a1 over a3 lambda minus a naught over a3. And so if you multiply that whole thing by a3, you'll get negative times the polynomial that you started with, right? Negative p. Which means that the roots, multiplying by a3, which is a non-zero real number, and multiplying by negative 1 doesn't change the roots. And so it's true in this case that what you'll get is you'll get a non-zero scalar multiple of the polynomial that you want. So the roots of that polynomial are exactly the eigenvalues of this companion matrix. Okay, that's the 3 by 3 case. What about the 4 by 4 case? I want to keep it on the same page so that we can compare and look, right? So now let me just start by putting my negative lambdas. This thing will be negative a3 over a4 minus lambda. I'll have 1s underneath my lambdas. Whoops. I'll have 0s everywhere but the last column, where I'll get negative a naught over a4, negative a1 over a4, negative a2 over a4. This thing. And again, I'll take a cofactor expansion along the last column. What do I get? Okay, now I'll get positive a naught over a4 because the minor map goes, right? Plus, minus, so you have to take negative that coefficient, times the determinant of a certain matrix. Well, what happens when you strike this row and this column? You're left with exactly 1, 1s down the diagonal and negative lambdas above. Okay, then we'll have minus a1 over a4 times the determinant of a certain matrix. What is that matrix? We strike this row and this column. So we get negative lambda 0, 0, 0, 1, negative lambda, 0, 0, 1. Then we'll get plus a2 over a4, determinant of what matrix? Strike this row and this column. We're left with negative lambda 0, 0, 1, negative lambda, 0, 0, 0, 1. Finally, we're left with a minus negative a3 over a4 minus lambda times the determinant of a certain matrix. Sorry, this is going to be over here. So let's strike this column and this row, and you get negative lambdas along the diagonal with 1s underneath. Okay, well, what do you notice? If you look at the determinants of the matrices, they obey the same basic pattern that was happening above. This one is always going to be 1. Why is it going to be 1? Because of the pattern that you put in your companion matrix. If you lose the first row of your companion matrix and you lose the last column, you'll have 1s along the diagonal, nothing below the diagonal, and so it's a triangular matrix. The determinant is just the product of the diagonal entries. And just by the way we've constructed it, as you take the next term, you pick up an extra negative lambda along the diagonal, and the matrix still ends up being triangular. Right, let me just make sure that I've copied down everything correctly. Yes, okay, just making sure. So this thing has determinant negative lambda. This one has determinant lambda squared. This one has determinant negative lambda cubed because it has 3 negative lambdas along the diagonal. Okay, so the signs of our determinants are switching negative and positive because it's how many negative lambdas we have along the diagonal. But that's counteracting the signs from taking the determinant. And so the first 3 terms in this case, so the first d minus 1 terms, give you the constant term, the lambda squared term. And then the last term in this determinant gives us our lambda cubed term and our lambda to the 4th term because we have this extra lambda sitting in the bottom slot of the column. And then if you just multiply the whole thing by a4, you'll see that you get exactly the terms a0, a1, a2, a3, a4 on the powers of lambda. Okay, so you can prove using induction that the determinant of the matrix that you get when you strike the ith row and the ith column ends up being lambda to the I minus 1. Negative lambda to the I minus 1, I should say. That's the thing that you could actually prove. And then that would prove that the characteristic polynomial of this companion matrix is, in fact, up to a scalar multiple, the polynomial that you started with, right? Which is good, but this proof requires induction, and it's a little bit not that fun to do, I think. Okay, so then use induction once you sort of understand what the pattern is. Okay, again, the next thing we're going to do, we're going to try to understand in a different way why this is true, but hopefully you can see that there's a way to just mechanically do it using induction. That's maybe not the most fun thing ever, but you should try to do this. Okay, but now I want to go into the optional section in the notes on quotient vector spaces, because I think it's a very important abstract topic that's not covered in 308, and even if what you're interested in is applications, if you want to read papers in machine learning or something, they will sometimes use quotient vector spaces, and if you've never seen one before, it can be very confusing. Even after you've seen it a couple times, it can still be confusing, actually. So I would like the first time to be maybe in this class. You may have seen them in 340. Okay, so our new topic is going to be quotient vector spaces. Okay, and the warm-up is a good one because it's one that hopefully we're all familiar with, whether we took 300 or we took CS classes, which is the integers mod 5. Okay, and we'll see that we can do something similar for vector spaces, and then we can do something similar for the polynomial ring in one variable, R adjoint X. Okay, and the point is that the set of integers mod 5 contains 5 elements, right? So the set of integers mod 5 denoted usually like this, z mod 5. You might also see, depending on who you are, you might see this written as z mod 5z. That's the same thing, but we'll stick with z sub 5 here. Is the collection has 5 elements, the equivalence class of 0, the equivalence class of 1, the equivalence class of 2, the equivalence class of 3, the equivalence class of 4. Sometimes, depending on who you are, you might see this as 0 bar, 1 bar, 2 bar, 3 bar, 4 bar. Okay, the point of the notation is these aren't integers. 2 doesn't represent the integer 2, it represents a whole equivalence class, either brackets 2 or 2 bar. Okay, and how do you construct them? You construct z5 as follows. If a is any integer, then you can write a as 5k plus r, where r is between 0 and 4. This is by the division algorithm. If you take any number and you divide it by 5, you can write it as 5 times an integer plus a small remainder, right? Like 103 is 5 times 20 plus 3, right? And you can make this remainder between 0 and 4 inclusive. Okay, and if there's a unique remainder, so this is unique, and if a is equal to 5k plus r, then we write a is congruent to r mod 5. Right. This is read, a is congruent to r modulo 5. Okay, it's the same thing as saying that a minus r is a multiple of 5. Right, so you can think of these equivalence classes as entire sets of integers. 0 brackets 0 is all the integers that are equivalent to 0 mod 5. What does that mean? That means that you can write them as 5 times k. In other words, the equivalence class of 0 consists of all multiples of 5. The equivalence class of 3 is all the integers that you can write as 5k plus 3. So there's 3, there's 5 plus 3, there's 10 plus 3, there's 15 plus 3, 20 plus 3, right? So the set of all integers congruent to 3 mod 5 is, there's infinitely many, 3 itself, because that's 0 times 5 plus 3, 8, 13, 18, dot, dot, dot. Also, there's a bunch of negative ones, right? So -2, -7, -12, -17, dot, dot, dot. All the things that you can write as 5 times an integer plus 3. And of course, these are all spaced out 5 apart, right? Because if you add 5, you get just a higher multiple of 5 plus 3. Okay, and what this does is this takes the entire set of integers. Right, here's the entire set of integers. Zero, 1, 2, 3, 4, 5, 6, -1, -2, -3. And what it does is it splits them into 5 different sets where you split them evenly apart, right? So like 0 is in the same set as 5, is in the same set as 10, is in the same set as 15. Maybe I should draw a couple more dots then. So this is -5, -4, -3, 7, 8, 9, 10 over here. On the other hand, 1 is in the same set as 6, is in the same set as 11, is in the same set as -4, right? 2 is 7, -3, 12, 3 is 8, -3. what I'm doing is I'm just coloring in integers the same color, except I've made a mistake here. Where's my mistake? My mistake is that I listed -2 twice, or I listed -3 twice. That's a bad mistake. Let me fix that. You should always remember that there's only one -3. Okay, that's better. Right, so I've colored in the same color all the integers that are congruent to one another modulo 5. And this equivalence class of 3, you can think of as the entire green set, every green integer. But kind of the point is that every single integer is going to be equivalent to one of these 5 special ones, right? And generally you choose 0 through 4 to be your representatives of your equivalence classes, right? So each integer is congruent to one of these representatives. Okay, so you start with an infinite set, the integers. You consider this equivalence class. What happens when you divide by 5? What's the remainder? Based on that, you can break the integers into 5 pieces, right? 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, based on what their remainder is when you divide by 5. And then every integer is in one of these representative equivalence classes. But the important fact is that you can actually do arithmetic not with integers, but with these equivalence classes. In other words, it makes sense to add the equivalence class of 2 plus the equivalence class of 4. Why? If you look at every single pink number here and every single white number, right? So the equivalence class of 4 I didn't color in. If you add those two things, you add a pink number plus a white number, you will always get a blue number, right? 2 plus 4 equals 6. 2 plus 9 equals 11. -3 plus 4 equals 1. If you add a pink number to a white number, you will always get a blue number. And so you could say that if you add the equivalence class of 2 to the equivalence class of 4, you get the equivalence class of 1. And this is exactly what you do when you do modular arithmetic, right? It's like you're setting 5 the same thing as 0. And so every time you reach a 5, you treat it as 0. So 2 plus 4 is 6, but it has a 5 in it, so you can subtract off the 5. It's the same thing as 1. It's in the equivalence class of 1. So you can add entire equivalence classes. And you can do arithmetic. Right? You can also multiply. Right? If you ever multiply a pink number times a white number, you'll always get a green number. So the idea behind quotient vector spaces is kind of similar. What you can do is you can take a vector space and you can split it into parts. And then you can consider each thing that you've split it into a vector in a different vector space, in a quotient vector space. Again, here we took the integers. The integers are a set of objects that you can add and multiply. And we split it into 5 parts, right? Huge parts, of course, right? All the green integers, that's one part. But we see that if you take these parts, you can actually add these parts together. I can add this entire equivalence class to this entire equivalence class. What we'll be able to do is we'll be able to take a vector space, split it into a bunch of different parts, and then instead of thinking about vectors, we can think of each of the huge parts of this vector space as a vector itself in a different vector space. Okay, that probably means nothing to you if you haven't seen this already, so we should start with the easiest example, which is quotients of R2. Okay, and the nice thing about R2 and R3, which we'll see in a second, is that you can actually picture it, right? So R2, we're used to thinking of R2 as this vector space, where every point in this picture is a vector. Okay, now recall that every subspace contains the origin. Right, so let me draw in a subspace. It'll contain the origin. Here's my subspace S. Now, there's no way to break up R2 into a bunch of subspaces that will cover R2 in the same way that we broke up the integers into a bunch of subsets that covered the integers, right? Because every subspace contains the origin. They'll all intersect in something, which isn't what was happening with the integers modulo 5. But what I can look at is I can look at all the lines that are parallel to S, right? So here's S. Here's a line that's parallel to S. This thing is not a subspace, right? This is not a subspace. All it is just a subset of R2. But I can consider every single possible line that's parallel to S. And if I did that, I would actually break up R2 into infinitely many pieces, but each of the infinitely many pieces would be like a one-dimensional line. Right, so that's what I'm going to do. So let S be a subspace. This is going to work in general. So that's why I said V rather than R2. Now, given a vector V in V, we define the following thing. V plus S is going to be the set of all vectors that look like V plus the vector S, where S is an S. Okay, so S is our red subspace here. Let's let V be this vector here. Then this subset V plus S means you take the vector V and you add every possible vector that lives in S. So the 0 vector lives in S, so this is V plus 0. Also, this vector here lives in S, so if I add it to this vector, I get this point. And hopefully it's clear that if you add every vector in S to this vector V, what you get is you get this entire blue line. This thing is V plus S. That's in blue. Okay, and then if I take another vector, one that goes here, call it W, this set is W plus S. Okay, in other words, what this is this is just a translation of S by the vector V. Right? This is sometimes called, this kind of subset, this is just a subset, right? So this is just a subset. But it's sometimes called an affine subspace. An affine subspace is basically a subspace that's not required to contain the 0 vector. It's a translation of a subspace. Okay, another thing to notice is that this blue vector V is not the only vector that I could have chosen to get that blue line. Right, I could have chosen this vector, call this vector V prime, and if I add every vector in S to V prime, I'll get the same exact blue line. Right, so this is equal to V prime plus S. What I'm trying to point out here is the analogy to the integers modulo 5. When you took the integers modulo 5, you basically declared an entire set of integers to be the same thing as 0. Every multiple of 5 is like 0. And then the equivalence class of 1 is all the integers that are a multiple of 5 plus 1. Right? So you can think of, by analogy, think of this subspace S as like being the equivalence class of 0. Then this blue line is going to be something like the equivalence class of V. It's going to contain a bunch of vectors, but they're all going to be V plus something in S. Just like the equivalence class of 1 consisted of a bunch of integers, but they all consisted of 1 plus a multiple of 5. And so if you consider the space of all lines that are parallel to S, it's going to break our vector space up into a bunch of pieces, and we're able to consider those vectors in a different vector space. Okay. This is a picture of a quotient of R2 given by, well, we haven't seen exactly why it's a quotient yet because we haven't defined a quotient vector space. Okay. Now let's think about the picture in R3. Okay, so quotients of R3. Again, let's take any subspace that you want of R3. I should say really any proper subspace, because if you take all of R3 itself, you've already gotten every vector in R3. So I want to take a proper subspace. It could be either one-dimensional or two-dimensional. It turns out it's not very useful to take zero-dimensional either, just the origin. You could, but the quotient that you get would just be R3 itself. Okay, that shouldn't mean anything to you yet, but so R3 looks like this. And there are several choices of subspace that we could take. Let's do a very nice one. Let's take the xy plane. All right, so let's let S be the span of 1, 0 and 0, 1. Sorry, 1, 0, 0 and 0, 1, 0. Now, you can add any vector to every vector in S, right? So if you take this vector V, and I look at what happens if you add every vector in S, what you'll get is you'll just get a flat sheet lying above that intersects V. This is V plus S. And again, if you take another vector W, maybe we can make this one go down this time. What you'll get is you'll get a parallel flat sheet lying underneath. This is W plus S. So you can take all of R3 and you could split it up into a bunch of things that are parallel to this two-dimensional plane. And it turns out that if you look at the set of all of these parallel sheets and consider them each a vector, you will get a thing that is a vector space. So in order to understand that, we need the following lemma. Okay, so suppose that S is a subspace of V. Okay, so 1, right, and I've defined this set already. V plus S for any vector V is all the vectors V plus S, where S is any vector in S. Okay, and so here's some facts about this thing. V is actually in V plus S. This is not so hard to see. But here's a nice thing. If W is in V plus S, then V plus S equals W plus S. And 3, W plus S equals V plus S if and only if W minus V is in S. Okay, so let me give you some proofs and some intuition. Okay, so first of all, the first one says that the vector V, the blue vector V, actually lies inside of the blue plane which consists of every vector that's v plus something in S. But that's obvious because 0 is in S. Right? So the proof of 1 is really fast. V is equal to v plus 0. So that's certainly in the set v plus S. Okay, what is the second thing saying? The second thing is saying if W happens to lie on this plane, I shouldn't have given that thing the name W, but new W. If W happens to lie on this plane, and I look at W plus every vector in S, that will give me the same set as V plus every vector in S. Right? Why is that? Because if W is in V plus S, it means that W is equal to V plus S for some S. But now if I add any other S prime, then W plus S prime is equal to V plus S prime, and this thing is in S again. Which means that anything that you can write as W plus S prime, you can write as V plus something in S, and vice versa. So the set of vectors that look like V plus something in S is exactly the same set of vectors as W plus something in S. Okay, and in fact, it's true that you will only get W plus S equals V plus S if the difference of W and V lies in S. Right? So in this case, if you were to take V and you were to subtract off W, right? So that'd be going like this, minus W. It's like you're going up into the plane, the blue plane, and then you're going back down. You'll end up on the red plane. This vector here is V minus W. Okay, but the proof is in the notes. It's actually not that long. You should try to understand it. But let me try to tell you the analogy to the integers modulo S. This is modulo 5, I should say, okay? So the way to think about this, and I'll put this in green, is here V is going to be like the integers, and S is going to be like the set 0, 5, 10, 15, -5, -10. Okay, so S is a subspace of V. That's like saying, okay, I'll take this subset of Z consisting of all multiples of 5. Then my V plus S's, right? So what is the analog of V plus S? You take any number, right? V is going to be like a number, so let's say like 3, and V plus S is going to be like the equivalence class of 3. S is going to be like the equivalence class of 0, right? That's what our subset is. V plus S is going to be like the equivalence class of 3. Now, thinking of it like that, let's look at these three things, okay? So the first thing says that 3 is in the equivalence class of 3, which is true because 3 is 5 times 0 plus 3. What does the second thing say? The second thing says if you take any other number in the equivalence class of 3, if you take 8 or 13, and you look at the equivalence class of 8, it's the same thing as the equivalence class of 3. And the third thing says is that the equivalence class of 8 is the same thing as the equivalence class of 3 because the difference of 8 and 3 is a multiple of 5. Okay, so what this lemma is going to set up is the ability to take the set of equivalence classes of vectors, in other words, the set of all of the parallel planes, and be able to add planes instead of adding vectors. Just like in the integer case, instead of adding integers, you can add equivalence classes of integers. Okay, so this picture here is meant to be evocative of this picture here. Here, like our S is like the yellow points, and you can slice up the integers into a bunch of stuff that's parallel to the yellow set. Right? You have the entire yellow set, you shift it over, you get the entire blue set, you shift it over, you get the entire pink set. Here, like our yellow set is like the red subspace. And if you shift it, you get the blue subspace. You shift it, you get the green subspace. You can cut up the entire space into a bunch of parallel subspaces. Just like here, you can split up the entire set of integers into parallel subsets of integers. And you can add these things and do arithmetic with them, which means that you can add these planes and do linear algebra with the planes instead of with the vectors. And so our new vector space will be a vector space whose vectors are in fact planes that are parallel to S, because you can add them and you'll be able to scalar multiply them and turn them into a vector space. That thing will be a quotient vector space. Okay, see you next time for more on quotient vector spaces.